by singing National Anthem of Indonesia, Indonesia Raya. All of guests are expected to prepare. By singing National Anthem of Indonesia, Indonesia Raya. All of guests are expected to prepare. Ladies and gentlemen, now we invite Dr. Insinyur Triwayu Hadianto, STMT, for the opening speech. To Mr. Triwayu Hadianto, time is yours.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Honorable Professor Hiroshi Onishi from Kobe University, Japan. Honorable the head of the Chemical Engineering Study Program, Mr. Boy Fahri. Honorable colleagues of the Chemical Engineering Study Program, Faculty of Engineering, University of Jember, and honorable my students of the Chemical Engineering Study Program, Faculty of Engineering, University of Jember. Also, webinar participants, lecturers, and students who may be from outside the University of Jember. Alhamdulillah, this morning we can meet in healthy condition to be able to study together and attend a guest lecture that will be presented by Professor Hiroshi Onishi from Kobe University. This activity aims to be able our insights and increase our knowledge related to chemistry, especially about catalyst technology. Greetings and my best regards to Professor Onishi, who has taken time to be able to share his knowledge with all of us. Even though in the situation of the COVID-19 pandemic, we can still work to improve our performance and increase our knowledge. When the COVID pandemic finishes, we will be able to meet and continue with collaborative activities between the two institutions. I hope and please, if there is a free time for Professor Onishi to come to Jember in Indonesia to know more closely about the chemical engineering in University of Jember. This activity is also collaboration with the International Office of the University of Jember, together with four universities abroad in Japan, England, Thailand, and Australia. Finally, congratulations and on participating in the webinar and representing the committee. I apologize if there are any deficiencies in this activity. Please let me to open this event by saying Bismillahirrahmanirrahim. International guest lecture officially has opened. Thank you very much and welcome to join this webinar event. The time I return to a committee. Thank you very much.
The speech delivered by Dr. Insinyur Trihwayu Hadianto, STMT. Thank you, sir, for your speech. Ladies and gentlemen, now we are coming into the main point of this event, the International Lecture Series, Chemical Innovation for Sustainable Future, and Series 1 about semiconductor photocatalysts for artificial photosynthesis, which will be guided by Hanggara Sudrajat SSK MH PhD. To Mr. Hanggara Sudrajat, time is yours.
Thank you, Samantha. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone, and welcome to our international lecture series, Chemical Innovation for a Sustainable Future. I'm Hanggara Sudrajat from the Department of Chemical Engineering, Universitas Jember. I'm the moderator of this first series of our international lecture series today. This event is brought to you by the Department of Chemical Engineering, Universitas Jember, in collaboration with Faculty of Engineering and the International Office. First of all, I'd like to thank the Dean of the Faculty of Engineering, Dr. Insinyur Triwahyu Hardianto, and the Head of the Chemical Engineering Study Program, Dr. Insinyur Boair Fahri. Also, of course, I would like to thank and welcome our honorable guest lecturer, Professor Hiroshi Onishi. So, speaking of this international lecture series, the purpose of this event is actually to bring the state of the art or the latest progress in chemical science and engineering research for achieving sustainable future. So we really would like to hear from you all and would like to include your voice in the discussion section. So kindly ask questions, share comments, even challenge the proposed ideas at any time during the lecture. So you can ask directly to Professor Onichi or use the question link, which will be shared by the host or co-host in the chat section of this Zoom meeting room. At this point, I'd like to introduce you, our honorable guest lecturer, Professor Hiroshi Onishi. He is a professor of physical chemistry from Kobe University in Japan. He has been a fellow of the Japan Society of Vacuum and Surface Science, and also the editor of the Surface Science Reports, a very prestigious international journal. He received his PhD from the University of Tokyo in Japan. His major research interests are in molecular science at the interfaces and mechanistic aspect of catalytic reaction. So the title of his lecture is Semiconductor Photocatalyst for Artificial Photosynthesis. So Professor Onishi, time is yours.
Okay, thank you very much. So I'm Hiroshi Onishi. So I now turn on my image. Okay. So I hope now you can find my face and my room in your screen. That's all right?
Yes, very clearly.
And then, so I should share my PowerPoint files. Let me do so. Now my first slide is on your screen, or perhaps the dual screen is on. So I hope the only one, my first slide is on your screen. That's all right?
Yeah, we can solve.
Okay. Okay. So now I can start my talk. So first of all, thank you very much for inviting me to be here. So it's my great honor to deliver a talk as the first talk of your series of lectures, international lectures. So today I would like to talk about the semiconductor photocatalysts for artificial photosynthesis. I believe that my topic is along your topic of your series, so the sustainable developments, innovation and the developments. And the second slide. So now you are in Jembel or other cities in Indonesia, around here. And I'm in Kobe, one city in the Japan main island. So, and now I'm somehow the northeast of you, from you, and the distance from my city, Kobe, to your city, Jembal, is around 5,000 kilometers. Then the time shift is 2 hours. So now it's 1:15 in Kobe and 10:15 in the morning in Indonesia. And now temperature here in Kobe is around 20 degrees C and somehow rainy. So now the temperature is going down in my country. So now the deep fall. So my student talked to me that it is not so warm. So we should put the warming the laboratories from now on and so on. But I think that the temperature in Indonesia is much higher than 20 degrees C. Okay, so get into the real part. So energy is a very, very, very important for us because we are living every day and we need some energy. So the energy is definitely a requirement for our daily modern life on this planet. But the energy is not freely supplied from nature. For example, so the in my country, so 10 years ago, we had a very large earthquake. And then at that time, one atomic power plant in my country failed. And then now the situation is getting back. So everything is ordinary, even in the area of the atomic power plant failure. But on the other hand, so it is the number of atomic power plants available today is very limited in my country. 50 or more worked before the earthquake, and now just a few. I don't know, 2 or 3. Anyway, very small number of the power plants are working. So of course, so the electric power is deficient, and as a result, the price of energy accordingly increased. So this is one very simple example in my country, but the situation is very similar in the world. So energy is not free, we should pay for, but the price should be large. So so we need another energy source. So one possible source is our sun, the sun. So irradiation from the sun to the surface of this planet is very large amount. So 3 times 10 to 24 joule per year. And on the other hand, so we consume energy 4 times 10 to 20 joule per year. So still there is a 4 orders of magnitude difference. So this means that when we are able to convert the energy from the sun to some form convenient for our purpose, so the energy problem on this planet is definitely relaxed. So the how to harvesting solar energy. So the one major principal way is natural photosynthesis by plants, green plants. So in the green leaves, the carbon dioxide and water and sunlight produces, say, organic materials like scrolls. And the foods and the fuels, everything we can get from this natural photosynthesis. And the second column, second line, solar cells. This is artificial. Probably the first way of artificial solar energy harvesting, and very simple. So just putting a solar light, then get the electric current to. So, and these solar cells are almost available, but it is not enough to replace the large power plants, or it is not enough to replace gasoline stations in our cities. So the last one, the artificial photosynthesis provides one alternative way to get the good energy in a sustainable form. So by now, 2 main reactions are recognized in this field, artificial photosynthesis. The first one is the water splitting to make hydrogen gas. The water and sunlight and some photocatalysts, then we can get the hydrogen and the oxygen. So this is the stoichiometric splitting of water. So nothing other than hydrogen and oxygen comes out. So this is the one way to get the sustainable energy source. So the hydrogen can be used as a fuels. And the other stream, this is a relatively new comparing to the water splitting. So the new way is a carbon dioxide reduction. So carbon dioxide, water, sunlight, and some good photocatalysts. Perhaps we get some reduced carbon dioxide. This means that some organic compound. So natural photosynthesis provides us, say, very complicated organic compounds, say the scrolls and so on. But the artificial photosynthesis, CO2 reduction, now the people in this area has a target of to make some say carbon monoxide or something like that. Very simple, but the reduced carbon dioxide. So there are these 2 mainstreams. And today I focused my talk about the water splitting reaction, the fast route, because the water splitting reaction is at this moment, by now, we get a relatively good photocatalyst. Already we get some good photocatalysts, not yet applicable to the industry, but we found a good candidate. And the CO2 reduction just started in recent years. So still the reaction rate is still very low. So it is not easy to get the scientific insight from the second reaction. So I'd like to focus my talk today to be the first one. So the overall water splitting to make hydrogen and oxygen. So before going into detail, so let me make a brief summary what the history of photocatalyst. So because Hangara kindly informed me that today many students are now join my lecture. So I prepared some slides for not professors but students. So the semiconductor photocatalyst was born in Japan, honorably in my country. So Kenichi Honda and Akira Fujishima, they are the two inventors of the semiconductor photocatalyst. They found and reported their achievement in 50 years ago. Honda sensei, Professor Honda, passed away 10 years ago. And Fujishima sensei, Akira Fujishima, Professor Fujishima is still very active. And still, I believe that he is working in his laboratory somewhere. And please allow me put a small story about me. And I'm now 57 years old. And when I was an undergraduate freshman of the University of Tokyo, this was 40 years ago, perhaps. 40 years, nearly 40 years ago. At that time, so the Honda sensei and Fujishima sensei, Professor Honda was a full professor in the University of Tokyo, chemical engineering department, and Fujishima sensei was associate professor there. And they opened their laboratory to a freshman, and they invited a few undergraduate students to stay their laboratory for 1 week in the summer vacation season. And at that time, I applied to join this activity, but of course, at that time, I didn't know who is Honda sensei, who is Fujishima sensei, and I have no idea about the photocatalysis. So there are many laboratories to receiving the undergraduate student, and just so by random selection, I joined their laboratory for a week. And so this was the first meeting of me to these great senior professors. Anyway, so they found photocatalytic phenomena by using titanium dioxide. This is a white solid, inorganic materials like ceramics. And
my stories.
I hope that you know what is the semiconductor. So semiconductor has a conduction band and valence band in electrical structures. And this is also the case with the titanium dioxide. And when they irradiate their titanium oxide with ultraviolet light, they can excite electrons originally in the valence band to the conduction band. This is a electron excitation induced by light irradiation. As a result of this excitation, one electron appears in the conduction band. This means that this electron has a very high power to reduce something. And here the one hole, positive hole. So this means that before excitation, there was one electron. But after excitation, that electron went into the conduction band. So there is an electron vacancy here. So we recognize this electron vacancy as a hole, positive hole. And this positive hole has a very strong power to oxidize something. Then when the water is split on this material, so this electron is used to reduce water to make hydrogen. So converting water to hydrogen is a reductive reaction. And on the other hand, so the water should be at the same time oxidized to make oxygen. So this is very, very important principle of the photocatalysts. So we always produce one electron and one hole. And in this water splitting reaction, we need just hydrogen as a fuel. We do not interested to make oxygen. So because oxygen is everywhere, but hydrogen is rare. So this is a reason why we should find a good way to produce hydrogen. But when we use photocatalysis, even we are interested just in hydrogen, we also take care of producing oxygen. If water oxidation to oxygen does not take place well, hydrogen production also does not take place. So we should take care of the pair of reactions. One is reduction, the other oxidation. This is a very fundamental principle when we utilize the photocatalysis for some practical purpose. The solar hydrogen, so we get some good photocatalysts, then water makes hydrogen and oxygen. And the vertical scale provides a Gibbs energy. So I expect the students know what Gibbs energy. So when I talk this topic to high school student in my country, I cannot use a Gibbs energy. So at that time, I just put here just energy. But because you are a chemical engineering department, so now today I can use the Gibbs energy. So sunlight put Gibbs energy to water to make the high Gibbs energy state. This means hydrogen and oxygen. So this is an uphill reaction. So climbing up a hill. What hill? The hill of Gibbs energy. The Gibbs energy comes from sunlight. And once we get the hydrogen and oxygen, it is relatively easy to make everything reverse. So starting from hydrogen and oxygen to make water. So this is a downhill reaction. So climbing down of a hill of Gibbs energy. So this is a very easy reaction. And then we get the heat, if we like, and we get the current when we need, for example, by using fuel cells. So climbing down or climbing up. So this is a simple reverse reactions. And we can expect that climbing up a hill is more difficult than climbing downhill. So this is a reason why the water splitting by using photocatalyst is not an easy reaction, because this is one of uphill reactions, and uphill reaction is always difficult to achieve. Hydrogen can be produced other than the from the source other than the sunlight. So at this moment in industry, we get a large amount of hydrogen every day, but these comes from fossil fuels. The two main streams, the one start from coal, solid carbon, and water. So we can make a hydrogen, a CO and hydrogen. And we can use this hydrogen for some purpose. And otherwise, starting from natural gas, methane, the methane and water, we get more hydrogen and one CO. And also these CO product CO product can further be converted to hydrogen by reacting with water vapor. So CO and water makes a CO2 and hydrogen. But by using these coal-induced or natural gas-induced conversion to make hydrogen, at the last, we should always produce carbon dioxide. So starting from carbon to ending up carbon dioxide, or starting from methane to ending up a carbon dioxide. Anyway, this provides the conversion of fossil fuels to produce hydrogen carbon dioxide. So this is not a true CO2 free conversion. So when we split the water to make hydrogen, well, so this process is completely free from CO2 production. But still, this is not really achieved in a large scale, in a practical scale. Okay, this is these slides showed you the background of hydrogen fuel and also the background of semiconductor photocatalysts. Then let me go into the more photocatalyst research. There are a number of the good photocatalysts, but today I focus to one of them. So the sodium tantalate. This is a inorganic ceramic containing sodium, tantalum, and oxygen. And this is a very good photocatalyst invented by Professor Kudo and co-workers 20 years ago. So this is a now well-known photocatalyst. And by using this, the apparent quantum yield of this water splitting reaction exceeded 50%. So what apparent quantum yield? So we need 4 photons to split one water, no, sorry, 2 photons. We need 2 photons to split one water molecule to make 1 hydrogen and half oxygen molecules. When we prepared ideal, perfect photocatalysts, so no energy loss. So still we need 2 photons to split 1 water molecule. And apparent quantum yield 50% means this photocatalyst requires 4 photons to do so. When the photocatalyst is perfect, this quantum yield goes up 100% unity. Unity means every photon comes into the reaction vessel are utilized to make hydrogen and oxygen. So still this 50% yield is pretty high. So I remember when they provided this series of photocatalysts, so everyone in this field, in the Japan and some other countries, were surprised because of 50%. Before that, 5% very good, 3% excellent. But 20 years ago, they found 50% is available. So this was a very surprising for us. So this is your so this is a photograph of their demonstration. Now this is a glass vessel and the water is inside, and here the metal plate here, and these white area, so they put their photocatalyst, sodium tantalate. So white particles are here. And then light comes from the top to irradiate the photocatalyst. And I hope that you can recognize these bubbles in water. Bubbles are coming up. And these bubbles are hydrogen and oxygen mixed gas bubbles. So now 20 years ago, they provide a good photocatalyst to make hydrogen and oxygen bubbles by using photocatalytic water splitting. So this means that this demonstrated that efficiency, their photocatalysts are very efficient to this reaction. After that, so many photocatalytic materials were found in a similar sense. So the first column shows that the first one, sodium tantalate. This is the main material of the semiconductor, and they put a small amount of lanthanum cations. So in this area, this means we recognize this the lanthanum doping to sodium tantalate. And then they get the quantum yield around 50%. Then soon later, the same group found calcium, strontium, or barium doping to the same host material, found a very similar quantum yield. Some years later, a different group in Japan found zinc doping to gallium oxide presented an even higher quantum yield for the water splitting, 70%. And finally, this year, this is Domen-san. He's a very famous photocatalytic researcher in my country. And they prepared a very good photocatalyst using a strontium titanate doped with aluminum cations, and they put some other materials to modify the photocatalyst, and finally they get the 96% quantum yield. This is almost unity. So we cannot ask them even higher. So 96 is almost unity. So this what tells this slide to us. The first thing is water splitting is not difficult reaction right now. This was difficult 25 years ago, but now by using these materials, we can get a very high quantum efficiency, 50, 70, or even 100%. But one very major problem remains here. These materials are always wide band gap. So we need ultraviolet light to excite these photocatalysts to make hydrogen from water. strontium titanate, gallium oxide, and sodium tantalate. Always we need an ultraviolet light. So this is the reason why by using these materials, we cannot produce hydrogen from solar light. So the ultraviolet light in the solar radiation is very limited. Very small amount of ultraviolet light is available on the surface of this planet. So when this reaction is driven by a visible light instead of ultraviolet light, so true solar hydrogen plants are produced somewhere, then we get a large amount of hydrogen from solar light harvesting. So this is a current situation of the water, the situation of the photocatalytic water splitting. And the secondary, as a scientist, so we recognize that always metal cation doping to host metal oxide provided the key to increase the apparent quantum yield. Of course, Kudo-san, they first prepared pristine, pure sodium tantalate as a photocatalyst, and they get some results. But later, they found by putting some small amount of lanthanum into the host material, the quantum yield increased much. And this is also the case with other materials. Always putting some metal cations, heterometal cations, was very good to increase quantum efficiency. So in the scientific question, what happens here? So there should be something very general, and something very good. So this is our fun to find what happens there. So we started our research, say 15 or 20 years ago with this series of photocatalysts, so sodium tantalate. And this table shows the reaction rate, water splitting reaction rate of what metal cations were doped into sodium tantalate. The lanthanum doping was the champion, the very good photocatalytic reactions. But still, barium, strontium, calcium doping increased the reaction rate compared to the pure sodium tantalate. So we decided to focus on the strontium doping to sodium tantalate to find why strontium doping increased sodium tantalate, the water splitting efficiency on this material. So the first question at the start point is doping with guest metal cations, strontium cations in this case, increased reaction rates on a photocatalytic water splitting. Why? This is a fundamental question to be answered. The first experimental tool was infrared absorption. So infrared absorption measurement of the photocatalysts. So the green area is a valence band of sodium tantalate, and the yellow area is conduction band. And when we irradiate the photocatalyst with ultraviolet light, one electron is excited from the valence band to the conduction band. And this excited electron can further absorb infrared light. So this means that if this is true, we can monitor how many electrons are in the conduction band by observing infrared absorption. when infrared absorption by the excited electrons are large, we know a large number of electrons are excited. So this was the case. The right-hand panel shows the infrared absorption spectrum of sodium tantalate photocatalysts. So the horizontal scale shows that the wave number starting from 400 wave number to 1000, 4000 to 1000 wave number. This is a mid-infrared region. And the vertical scale is a absorbance change induced by UV light irradiation. So positive absorbance change means by irradiating ultraviolet light, infrared absorption intensified. So these colored lines spectrum shows the experimental results. When we irradiate the photocatalyst, say, look at the blue one here. So these blue spectrum appeared. This means this form of infrared absorption appeared induced by ultraviolet light radiation. And this spectrum can be assigned to electron absorption. So this electron absorbs IR light in this way, then present this form of absorption spectrum. So then we can know how many electrons are in the conduction band by monitoring the absorption intensity. So of course, many electrons or many holes in the photocatalyst particles is good to make large amount of water splitting, because two electrons or two holes are required to split one water molecule. So when we should split a large number of water, of course we need a large number of electrons and holes. So, but before this measurement, there is no way to quantify how many electrons are available in the photocatalyst. But by using infrared absorption, we can quantify this photocatalyst provides a very large amount of electrons. Or this photocatalyst is not good because this photocatalyst just provides a very limited number of electrons. So now we can use IR absorption to quantify the number of excited electrons. Then we apply this method to strontium doping to sodium tantalate. There are a number of IR absorption spectra, and this black line runs bottom of the figure. This means that this black line comes from the pure sodium tantalate, not doped at all. And the pure sodium tantalate provides very small amount of infrared absorption. This means the number of excited electrons in this compound is limited. And put small amount of strontium, how small, say around 1 mole percent, strontium cation doping, the infrared absorption rising up in this way. And say so 1.5 mole to around the 2% doping, the very intense IR absorption appeared. And by applying Lambert-Bell approximation, the area intensity of the IR absorption should be proportional to the number of the excited electrons. Then we measured the number density, the area of the absorption spectrum, and we found the doped sample, optimally doped sample photocatalyst presented the 180 times, nearly 200 times enhancement of the number of excited electrons comparing to the pure sodium tantalate. So now we found, so how many electrons excited is the key, how this photocatalyst is efficient for water splitting reactions. The very simple relationship. Many electrons produce many hydrogen. Very simple. So now our question is updated. Doping with guest metal cations, strontium doping to sodium tantalate, limited electron hole recombination. So electron hole recombination is a way to reduce the number of electrons. So by using infrared absorption, we found the number of electrons much enhanced by strontium doping. So this means strontium doping limited electron hole recombination. So our question is updated. Why this happened? Why strontium doping limited recombination? So to discuss this, we wanted to know the precise chemical structure of our photocatalyst. So more specifically, where strontium cations are placed in the host crystals. So the sodium tantalate has a perovskite type structure. So large sodium cation here, blue spheres. And the small tantalum cations are presented in red spheres, and the blue green balls are oxygen anions. So this is a typical perovskite structured lattice. And now we put small amount of 1% or 2% of strontium cations into this lattice. So naively, we expect that we can expect the strontium cation should be replace sodium or tantalum cations because they are cations. So it should be difficult to replace anion by cation. But no one knew at that time where strontium cations were. So strontium cations can replace sodium cation or can replace the tantalum cation. Of course, we can expect what happened there by using ionic radius in literature. Sodium radius around 0.14 nanometer. This is a relatively large, so sodium cation is relatively large cation comparing to the tantalum cation. Tantalum cation is 5 times ionized, so the very small 0.06 nanometer because of high positive charge. And the strontium cations, the radius of the strontium cations are around 0.14 or 12. So just looking at this table, we can guess strontium can replace the sodium cation because the size of the two cations are very similar. So it should easy to replace one sphere with another sphere of the similar radius. So people, researchers naively believed that strontium cations should be here by replacing sodium cations, but no experimental evidence at that time. So we decided to confirm and found this was not the case. So strontium was in sodium place and also at the same time simultaneously tantalum site. So this is a very surprising for us and also the researchers in this area. So how to do this? Here we use the X-ray absorption spectrum. Here the strontium cations here, and X-ray comes on, and they hit the 1s electron of the strontium cation. And when X-ray has a very large energy, so this electron excited, so kicked out of the cation. So these green circles represent the wave function of excited electrons. Originally, one electron is in the 1s orbital, and this electron was excited by X-ray to a free electron, kicked out the cations. And the free electron wave function, spherical wave function, is propagating in this way. And from the distance from here to there, the distance from the two green circles represents the wavelengths of the wave function. Then this spherical wave expanding in space, and there is a neighboring atom in the photocatalyst crystal, neighboring atom, perhaps an oxygen atom, oxygen anion. Then the expanding green wave function is scattered by the neighboring atom. As a result, the spherical wave of represented by blue circle, scattered wave propagating from the neighboring atom center in this way. So please imagine you are swimming in a pool with your friend, and you are here, and your friend is here. You are the strontium cation, and your friend is a neighboring atom, and you are making wave in the pool, the water surface in the pool. Then the wave propagating in a circular way. Then when the wave get to your friend, even your friend is not intentionally excite the wave, your wave is scattered by your friend and getting back to you. So this is what happens in a pool, and this view graph shows what happens in the photocatalyst crystals. Then when the wavelength of the wave function is this number, so now the green circle and the blue circle hit one common place. This means that these two wave functions are in phase. So when this happens, X-ray absorption coefficient is large. But when this doesn't happen, so here the wavelength is different. So these two green and blue wave functions are out of phase. Here, X-ray absorption is limited. So, and the important thing here is out of phase or in phase is determined by the distance from the strontium cation to the neighboring atom. So by using this phenomena, I do not want to go into detail how to do so, but as a result, finally, we get the distance from this strontium cation to the neighboring atom by observing X-ray absorption spectra. So we applied this method to determine our strontium cations in the sodium tantalate. As a result, finally, we found the So our strontium cation is in sodium place, at the same time at the tantalum place. Not just sodium, not just tantalum. Both two elements are simultaneously replaced by strontium cations. So this is a result from the X-ray absorption analysis. So now another question comes. So strontium is doubly charged. Tantalum is 5 times charged. Sodium is singly charged. So the positive ionic charge is different. So putting strontium to sodium or and tantalum, the cationic charge is changed. How many strontium cations are doped? So always cationic charge and anionic charge should be balanced. So to compensate the positive charge difference, so the number of anions should be changed or not. So the answer is not. So this is a X-ray diffraction, very fundamental way to know the lattice size of the sodium tantalate. And this is the diffraction patterns. And putting strontium into sodium tantalate, the diffraction peaks shifted to low 2 theta direction. So this means that putting strontium into sodium tantalate, the crystalline lattice expanded. Larger lattice presented a small 2 theta angle for diffraction peak. And we quantitatively analyzed. So the unit cell volume determined from the XRD as a function of strontium doping concentration. So these blue spots presented experimental results. And as you see, these results are well fit by a straight line from here to there. That is unit cell volume straight linearly dependent to the concentration. This means there should be a solid solution. So here the one component of solid solution is a pure sodium tantalate, and the other component is a strontium tantalum oxygen. This is another perovskite structure. Well, known compound and in a perovskite structure lattice. So by making the sodium solid solution of the two compounds, we can get a solid solution of any desired concentration. So we found that. So this happened. So and these two compounds, one extreme is a sodium tantalate and the other extreme is a strontium tantalum oxygen. But these two components has no oxygen vacancy. So this means that any solid solution composed of the two compounds is not is free from oxygen vacancy. So by putting strontium as you like, but you do not need to any oxygen vacancy. So this is I think that this is one reason why strontium doping to this compound is good for the photocatalytic reactions. Okay, so now we come to almost the final part. So our question was further updated. So the current question is, the solid solution, sodium tantalate and this compound solid solution, we found this solid solution provided was present in our photocatalysts. And the question is why this solid solution limited the combination to increase water splitting rate. So here we compared the how to prepare our photocatalyst by changing the time for heating. So this type of photocatalyst is very simply made. So make a mixture of starting materials, strontium, sodium, and tantalum. Then make a mixture in a crucible and heating up in a furnace in air, say around 1000 degrees C. In this case, 1400 Kelvin anyway. And we prepared 4 different photocatalysts, 4 different but one common strontium concentration. We fixed strontium concentration at 2% and changed how long we heated up the photocatalyst in preparation, just 1 hour for 60 hours. And we compared the infrared absorption induced by UV light radiation. I hope you remember that infrared absorption, strong absorption indicated a large number of electrons are available in the photocatalyst. So we found 1 hour heated sample presented the largest number of electrons. And by heating up for a long time, for 60 hours, the number of electrons going down. So we found the number of electrons were very sensitive to the heating time. And the short heating time was good to increase the electron number. So why? So we did a transmission electron microscope observation. So these are microscope view graphs. So we can get the square particle, and also we get a very good, well-ordered atoms in the crystal. And further, we conducted the elemental mapping. So this means the local mapping, the local concentration of tantalum, oxygen, sodium, and strontium in one particle at the same place. And we found that tantalum, blue tantalum, red oxygen, and yellow sodium distribution map was uniform. Everywhere, the same concentration in a particle. But just strontium, so in a green map, strontium concentration was enhanced at the surface, particle surface. I hope you can recognize here some intense green color is present at the surface of a particle. So this means strontium concentration is increased on the surface. And we measured the width of the increased layer, strontium enriched layers, the width of the strontium rich layer, and we found just a 3 nanometer, so very, very thin, 3 nanometer thick layer was strontium rich. This was observed at the 1 hour heated sample, and we compared the 60-hour sample heated photocatalyst, and we found no strontium enrichment. Strontium was uniform everywhere. So now these TEM microscope results showed us that strontium enrichment at the surface was the key to increase the number of excited electrons. So now we come to the final illustration. So by putting strontium cations into sodium tantalate, the strontium was enriched at the particle surface just to make a 3 nanometer thick strontium accumulation layer. Here, strontium concentration is large, and in the bulk particle, less. And by putting strontium cations, conduction band of the sodium tantalate lifted up by small amount. Then now we irradiate the particle by UV light, and electrons excited from the valence band to the conduction band. And excited electrons should move in this way because the conduction band is lifted at the surface, not lifted in the bulk. So there is a slope. So electrons should going down along the slope. This means that the electrons moved from the surface to the bulk of the photocatalyst particle. On the other hand, hole should be present here. And hole is not needed, does not need to migrate in this way. So hole should be present here, remain here. So hole here, electrons there. So electrons and holes are separated in space. So separated, the two holes and electrons separated in space is naturally difficult to make recombination because recombine one electron and one hole, always we need to make them together. But this view graph tells us that by doping strontium, electrons going in this way, hole does not, and so automatically electrons and holes are separated in space. As a result, no recombination. No recombination means the number of excited electrons increased. The increased number of electrons was good to make a water splitting reaction. Okay, so now that my story is ending up. My answer to the question is electrons and holes were separated in space at the graded junction. The graded junction means the strontium-rich layer at the particle surface and less strontium distribution in the particle bulk on the solid solution photocatalyst particles. So this is my story. And recently I prepared one review paper here, ChemSas Chem. And so what I talked to you today is a summary of what I described in this review paper. So when you are interested to more detail of the story, you can access this review paper. This paper is open access, so you can freely access this article everywhere. Okay, so today I talked about the photocatalyst for water splitting. And so at the final stage, I emphasized that the single nanometer scale, so 3 nanometer or 5 nanometer scale strontium enrichment at the particle surface was very important to control water splitting efficiency. So compare the size, characteristic size of the efficient structures. So proteins, these proteins are functional in natural photosynthesis. And the protein size is in the order of 10 nanometer. So these 10 nanometer proteins provided every good thing about the natural photosynthesis. And our artificial photosynthesis device, so photocatalysis is one of devices to artificial photosynthesis, is now we can control the 3 nanometer scale chemical structure of the photocatalyst particle, and this was very good to increase the water splitting rate. So now the size, I would like to show you that the characteristic length of the functional materials is very similar. So 10 nanometer in natural photosynthesis, and say single nanometer in artificial photosynthesis. So this infers us that as a chemical devices, so in a sense of chemistry, so single nanometer or 10 nanometer is a very important size of scaling. So I expect that, so how to precisely control single nanometer sized chemical structure provide the key to make something good in near future in photocatalyst and also other field of chemistry. So the top panel shows the artificial electric circuit. So and now the latest version is the circuit line width. The line width in electrical circuit in electrical device is around 10 nanometer, very, very small. So I think these 3 numbers are informative for us. So 10 nanometer or single nanometer architecture should be very important in many applications, many fields, many industries. So to support sustainable developments in our country. So please, so especially for the student, I ask the young student to put your eye what happens in a single nanometer or 10 nanometer scale. This should be good for making your future. Okay, so these results comes from the collaborations with many researchers, not limited to Kobe University. This view graph shows just the major partners of our research. And so Professor Hangara Sudrajat, so he was in my laboratory for 2.5 years, and he just went back to Jembel this April. And so he did a very good job when he was in my laboratory, and he already published 6 international journal papers about his work in my laboratory. So this was very good experience for me to have a young researcher from Indonesia, and I hope and I believe Hangara agreed me. And so I need more collaborations with everyone in the world, including Indonesia, to find a new question and new answer in semiconductor-based photocatalysts. So this is the final slide. Welcome to Kobe. So this statement, I asked Hangara to translate my message in newer language. And unfortunately, I cannot read out. But so just showing you at the end of my talk. So thank you very much for your attention.
So thank you very much, Professor Onishi, for your nice talk. So we know that after following his lecture today, we know that photocatalysis, also known as the artificial photosynthesis, can convert photonic energy, which comes from the solar radiation, to chemical energy, including hydrogen, as Professor Onishi pointed out, by using some semiconductor as a photocatalyst. And Professor Onishi mentioned that perovskite structure tantalates are quite promising photocatalyst material for that purpose. Of course, we have get some questions. Okay, we come to the discussion section. So here we have received some question. So let us share them. So for hosts, could you please show us the question that we collect? So here we will show some question that we have received from some of you. Hopefully we can see. Please wait a moment. Sorry, Onishi Sensei, could you stop to share screen?
Okay,
We will.
okay, I see. Okay, hi, yeah.
Okay, this is from Adam from Universitas Jember. Hydrogen can also be produced from biomass, which is biohydrogen. So what do you think about this technology compared to photocatalytic photosplitting that produce hydrogen?
Okay, I get it. So you are right. So today I focused on the overall water splitting to make hydrogen and oxygen. So and as I mentioned in the first stage, we want just hydrogen. We do not need any more oxygen. So but when we start from pure water, we should split completely stoichiometrically water to make hydrogen and oxygen. But there is a freedom to change the starting material. So when we change the starting material from pure water to organic materials containing water, say, so in a laboratory case, usually the methanol is frequently used. So aqueous solution, starting from aqueous solution of methanol, it is pretty easy, much easy to get the hydrogen bubbles. So here at that time, so say in the overall pure water splitting, we should oxidize water. We're not interested to oxidize water, but we should do so to get the hydrogen. But when starting from the methanol solution or organic material containing solutions, we do not need oxidized water to make hydrogen. And so as a result, so getting hydrogen from not from pure water is one practical way, provide a practical way to get the hydrogen. So I agree with this statement. So one problem to be considered is, so in this process, always we need some organic materials as a starting material. So getting hydrogen, we need some starting organic materials. So this is a kind of chemical conversion from the starting organic material to hydrogen as a last product. So this makes sense when we can provide starting material, some organic materials, steadily at that low cost. So this may make sense to get the hydrogen from, say, perhaps we can get the hydrogen from organic waste. So that's very good because starting materials waste is should be low price. But that this is some say limitation. So we always need some reactant as a starting material. But when the reactant is available, so that makes sense to make a hydrogen by using solar light. And at that time, the choice of photocatalytic materials is relatively free comparing to the pure water splitting. So there is a larger chance to get the good results. This is my answer. The next question, what is difference of hydrogen and nitrogen, both them from oxygen? If we produce a lot of nitrogen, is there any impact for it? I think that's all. Okay. Nitrogen is when we consider N2 molecule as molecular nitrogen, there is no interest to make nitrogen because a nitrogen is a very, very easily available in air. So, and that one thing is, so at the first part of my talk, I showed you there are two main streams in artificial photosynthesis. The first one is water splitting to make hydrogen. And the other relatively new route is CO2 reduction to make some organic materials. And actually, the third way is now being proposed. The third way is reducing nitrogen, starting from N2, reducing N2 to make something other than N2. What should be the product? Variable product, ammonia, NH3. So starting from nitrogen, ending up NH3. This makes sense in the industry because now we synthesize NH3 very large amount, very large amount annually because ammonia and NH3 is definitely needed to futilization. So the history of ammonium synthesis going back to Fritz Haber 1 century ago. Fritz Haber find how to make NH3 from N2 and hydrogen. So now still his process is going on and we get a large amount of NH3. But now some researchers, photocatalyst researchers are interested to replace this process by using photocatalysts. So N2 is available everywhere. And so nitrogen and water makes NH3. This is a dream process. So nitrogen is everywhere, water is everywhere, sunlight is everywhere. Then ammonium, NH3 should be everywhere on demand. But this should be very difficult process. So perhaps the CO2 as difficult as CO2 reduction, or perhaps more difficult than CO2 reduction. But that always, as a scientist, we should make a dream. In this sense, the nitrogen conversion to make ammonia, NH3, is a one difficult but attractive target of artificial photosynthesis. Thank you.
Okay, I hope this answered your questions. Can we move to another one?
Yep. Can photocatalysts be used to produce other variable chemicals and fuels? Yeah, so my answer to the former question makes partially answer this question. So at this moment, photocatalysts to make something variable is, say, making hydrogen, making CO2 reduction, possibly NH3. So these three, perhaps sometimes the hydrogen peroxide, 82O2. So it's so water in the water splitting. Sometimes we get a small amount of 82O2 in addition to 82 and O2. And when the hydrogen peroxide is a good reactant in chemical industry and a relatively expensive material. So perhaps the producing hydrogen peroxide is one of the possible application of the photocatalyst to make, in a sense of making variable materials. All right.
Okay. Thank you very much, Nisi Sensei. So we come to the next questions.
Okay, what is the limiting step in photocatalytic process mechanism that should be taken into account when trying to increase the quantum efficiency of the photocatalyst? Limiting step. Limiting step is electron hole recombination, always. So, so when we irradiate photocatalyst with photons, and this photon, so the one photon, okay, no, 100 photons are absorbed by photocatalyst. So 100 electrons and 100 holes should be present when the photons are absorbed. So because 100 photons, so 100 electrons and 100 holes. There is no exception. But sometimes we get 100 hydrogen, but sometimes we just get one hydrogen. What difference? So in 100, when we get the 100 hydrogen, very large amount of hydrogen, excited 100 electrons are fully utilized to make hydrogen. No loss, no loss. So 100 hydrogen comes out. But what happens when we get just one hydrogen? 99 electrons lost. How to lose? The way of losing is just one, recombination. So recombine with holes. So do nothing. So get into the original state. So always producing some products, in this case hydrogen, or recombination, get into the original state is competitive. So when we get a large number of products, we should win in the competition. And who is a competitor? Always recombination. So when we should get the good efficiency, we should speeding up the forward reaction. Forward reaction means how to produce hydrogen using electrons. So make electrons more easily to make hydrogen. So pushing up the forward reaction rate. This is one way, but the other way is limiting the competitive process. So when we prohibit the electron hole recombination. The excited electrons should always make product. So this is because there is a competition. So the electrons are asked himself, so reduce water or recombine with holes. So he should choose one of the two, no other choice. So, and we would like to him to make hydrogen. So we should ask him to not to recombine. So I hope this is an answer to your question.
Okay, thank you very much. So the limiting step is electron hole recombination. Okay. Come to the next question.
Price of photocatalyst. Say, at this moment, the photocatalyst for artificial photosynthesis is not commercial. Just researchers in universities of some institute are preparing by themselves. So they can not make a surprise. So when these processes are commercialized, the price of photocatalyst should be sensitive to the price of photocatalyst, the elements needed to make photocatalysts. So in this sense, tantalum is not good. Tantalum is say one of rare metals, and tantalum is somehow expensive comparing to other metals. But say now a strontium titanate is recognized a good candidate. So comparing tantalum, titanium is much cheaper. So, but anyway, so when the strontium titanate is commercialized, perhaps the price of the photocatalyst largely depend on the price of strontium or price of titanium. The cost for preparing photocatalyst is not. I don't think the cost for preparation of the photocatalyst is not so important. So because the photocatalyst preparation is not much complicated, just making say a mixture and then heating up and so on. Not so the photocatalyst preparation is much different from the state of the art inorganic synthesis or state of the art organic synthesis. Much easy way. So so this the price should be dependent on the price of the elements required.
Okay, thank you very much. Is there any question left?
From Osaka University. I have how many ways to control electron hole recombination? Which one is the best one? Yeah, so I think there are not. So I showed you today just one example. So in the metal doping, strontium doping to sodium tantalate, what happens there, and why electron hole recombination was limited. And I believe my answer to the strontium doping to sodium tantalate is correct. And also I hope the situation is very similar of doping, calcium doping to sodium tantalate and barium doping to sodium tantalate, because calcium, strontium, and barium are in the same column of the periodic table. But this does not mean this is the only scheme to how to restrict recombination. So for example, strontium titanate case, so recently Japanese researcher found the strontium titanate is very, very efficient. And they are proposing a different scheme, why the doping to strontium titanate is good for water splitting. So, and I think so. I want to say I'm right, they are wrong, and I hope so. When 2 or 3 or 4 schemes to enhance photocatalytic reactions, that's much better than just one is available. So I don't say I want, but I'm not sure. So we are so happy to have a number of schemes to increase photocatalytic reactions. I found one, and perhaps there are some other. I do not want to deny, but so sometimes I asked myself, so we are so happy so to get a number of different schemes to enhance photocatalytic reactions. Perhaps there are a number of, say, schemes to how to pushing up the reaction efficient. So today's scheme is good for sodium tantalate, and another scheme is for strontium titanate, and even other scheme it may be efficient for other materials. But today I do not say this is correct or not.
Okay. I hope this answer the question. Okay, maybe we still have some.
Yeah. Many electrons produce many hydrogen. Does this concept can work on sunlight too? I mean that does many sunlight can produce. Okay. So in principle, yes, I believe that many electrons leading up to many hydrogen. And how to make many electrons? Putting more light is a very simple way. So 100 photons should make 100 electrons. 200 photons should make 200 electrons. So in principle, so more intense light irradiation, even sunlight or even artificial ultraviolet light, a intense irradiation should lead to more hydrogen production. One thing is, but I do not mention that always proportional. When the light intensity is small enough, the relationship should be proportional. Twice intense, twice as large as a large amount. But I expect that 100 times intense, not 100 times, less than 100 times enhancement in hydrogen production. So why? Many electrons automatically requires many holes in the photocatalyst. And this means that much easy for recombination. So recombination is second order process. So recombination takes place when a hole and an electron get together. So the population, electron population and the hole population in one photocatalyst particle increased. So the chance of getting together naturally increase. So this means that there is a much chance to recombine. So putting more light, then this means that increasing the probability to recombine. So in a small light intensity, we expect the very little effect of the light intensity. So this means that reaction rate almost proportional to the light intensity. But this does not the case when we put a very intense light.
Thank you very much. Next question, we still have some.
Yeah.
Sorry for this. Okay.
A efficient photocatalytic reaction, there are some factors. One of them is the host material. My question is what the condition the host material? This is a very difficult question. I agree. No. Okay. So this is a question to be answered. So what host material is good? So I talked today, doping some heterocations are good, and what cations may be good. So today I skipped what host material is good. This is because I do not know. But in my opinion, so the good crystal structures, good means that say easy to be crystallized. So this is because real photocatalyst is always prepared. So when the photocatalyst is very delicate structure or composition, we need a much skill to prepare good photocatalyst. So this type of very complicated crystallographic structure is generally disadvantageous because no, it is not so easy to intentionally modify the host materials. So I think, or I like simple crystallographic structure. In this sense, perovskite structure is very good because the perovskite structure is one of the most simple crystallographic structure, so easy to handle. But I do not find reason why perovskite structure is good comparing to other structures. I would like to mention perovskite structured host material looks good because there is a good room to modify chemical composition or something like that. So a good freedom, large freedom to modify is may make the good result. But I do not have reason. By this reason, perovskite is best, should be best. So I don't. So this is just my. I like perovskite structure right now.
Yeah, hopefully perovskite structure is the best because we work in this material. Okay, so I think we can finish our guest lecture today. So finally, we come to the end of this first lecture series. We'd like to say thanks again to the guest speaker, Professor Onishi, for sharing important information about photocatalysts for artificial photosynthesis. We also thank all the participants for joining our event today. We do hope that our first international series will be beneficial for everybody. So before ending this section, let me share you for the second series. For the second series, it will be delivered by Dr. Irene Kara from Cranfield University in UK. So the title is Advanced Oxygen and Water Treatment, Recent Trends. So it will be on Monday, October the 26th, 2020 and 15th. So don't forget to attend. Okay, I put my role back to Samantha. So Samantha, please.
Okay, thank you, Mr. Hanggara. So ladies and gentlemen, finally we get to the last session to this event that is closing. As the Master of Ceremony, we'd like to give thanks to Professor Hiroshi Onishi as the speaker, to Dr. Insinyur Triwahyu Hadianto STMT as the Dean of Engineering Faculty Universitas Jember, to Insinyur Boy Arif Fahri STMT PhD as the Head of Chemical Engineering Department, and then to the audience entirely. May what we had conducted will be useful for us. If in guiding in this event, we made mistake or offend someone here, please accept our apologize. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you very much.
Yes, to all the audience are expect to turn on the camera because we like to have some photo shoot.
Yeah, we will take some picture for a souvenir or something like that. So please, please show your nice face.
Okay, can we start? Okay, 3, 2, 1. Again, 3, 2, 1. Again, 3, 2, 1. Again, 3, 2, 1. Okay. Okay. So thank you for the all audience, everyone. Thank you so much.
Thank you so much, Professor Onishi, for joining.
You're welcome, and it's my pleasure. And I was very happy to have a number of questions, probably from students.
Thank you very much. So let me close this event. So see you next time. See you in October the 26th.
Yeah. So.
Thank you, Sensei.
Thank you, and bye.
Thank you very much.